In today's lesson, we're going to talk about reaction rate and rate law, concentration profile and flow rate graphs, mole balances, and different types of reactors with their design equations. Let's talk about rate. Usually when we hear the word rate, it has to do with the speed at which something is happening. When scientists or engineers run a chemical reaction, obviously they want to be able to create their desired product. But in order to do so, they need to understand the different variables at play that might change how fast their product is going to be made. It is important to understand the effects of different variables on the rate, or speed, of a chemical reaction. But how do we measure exactly how fast a reaction is going? Well, rate of a reaction is measured using the number of moles involved per time and volume. We can write the rate for each individual compound in a reaction, as well as the overall rate law for the whole reaction. Rate is measured, as I wrote here, in units of moles per time volume. Moles are measured in moles, but time can be measured in seconds, minutes, days, hours, and volume can be measured in, for example, decimeters cubed, liters, milliliters, and so on. So for example, moles per liter second or moles per decimeter cubed minute could be possible units of rate. Now there are different ways to represent the rate. Let's say we take this example of making water from hydrogen and oxygen. In this course, the chemical compounds involved in a reaction usually don't matter, so they're denoted with letters. Here I've denoted H2 with A, O2 with B, and H2O with C, all while keeping these coefficients constant. A lot of times you'll probably see chemical formulas written out in terms of letters, such as A, B, C, and D, because the actual chemical compounds reacting are not going to be very important. So as we learn from general chemistry, the left side of an arrow is always the reactant side, and reactants are chemicals that are consumed. Rate can be denoted with a couple different terms. So usually reactants are the chemicals that are consumed. They have a positive rate of consumption or rate of disappearance because they are disappearing or being consumed. When we talk about products would have a negative rate of consumption or rate of disappearance because they're not being consumed, they're being produced. So the sign would be the opposite. Now when we talk about products will have a positive rate of production or rate of appearance or rate of generation. They're all the same thing. And if we talk about reactants will have a negative rate of production, appearance, /generation because reactants are not being produced, they're being consumed. So if we talk about the rate of any of our chemicals on the reactant side, it would be a negative rate. Here I've denoted R and P for reactants and products and when it would be positive and when it would be negative. Rate can be written in different forms. There is a way to equate the rate of every chemical in a reaction. So the way we denote rate for a specific chemical is by putting a subscript with its name. So if I'm talking about the rate of A, I'm going to put RA. Then we put equals RB equals RC. To equate the rates, the first thing you have to do is set the rate of every single chemical equal to one another. Then you need to put positive or negative signs depending on if your rate is talking about a reactant or a product. A and B are reactants, so I'm going to put a negative in front of them, and C is a product, so I'm going to leave it as is. Lastly, you need to divide each chemical by the coefficient in front of it. A has a coefficient of 2 in front of it, so we'll divide it by 2. B has nothing, which is just a 1, and C has 2. So I can read this as negative rate of A divided by 2 equals negative rate of B divided by 1 equals positive rate of C divided by 2. Or the rate of consumption or disappearance of A divided by 2 equals the rate of consumption or disappearance of B divided by 1 equals the rate of production, rate of appearance, or rate of generation of C divided by 2. This is useful when you have to solve problems where you are only given the rate of one chemical, so we can use this equation to find the rate of all the other chemicals in our equation. Now let's talk about the rate law. The rate law can be given as negative rate of A equals K times CA. This is generally for the first reactant, but remember, if you found the rate of A, you can find the rate of B and C and every other compound in your equation. This is the general rate law for the first reactant in a chemical equation, which is our A. Then you can equate the rest of the rates using this equation and find the rate of B and C. So R is the rate, which, as we talked about earlier, is measured in units of mole per time volume. K is the rate constant. This rate constant is usually given in your question, and the units of K are not fixed. They can change depending on what your units of CA turn out to be. Sometimes you might end up having a squared or a cubed. In that case, the units of your concentration would change, and that would also change the units of your K value. And Ca is concentration of your first reactant, A, and concentration is measured in moles per liter, which is also sometimes seen as a big M for molarity. Let's talk about how we can develop the rate law for this specific example, because as I mentioned earlier, the exponent on your concentration can change. Although this is the general form of the rate law, when we try to make our own rate law based off of an equation, there are some rules that we need to follow. So let's talk about that next. So the first step when we are trying to make our own rate law based off an equation we are given is that we need to look at our first reactant, A. The first step when we are trying to develop our rate law is to just write down negative R of your first reactant, which in our case is A. If it was anything else, then that's what you would put in your subscript. And it should have a negative in front of it because reactants are always consumed, equals K, and K is always going to be there no matter what as well. Now, we are going to write our concentrations, and this is where things are going to change. The rate law always depends on the reactants. The products do not matter. So we are going to write the concentration of every single reactant. In our general law, we only had the concentration of A, and I should note that this kind of reaction is just an A to B reaction because our only reactant is A, so only the concentration of A appears in our rate law. In this equation, we have both A and B as reactants, so we have concentration of A times concentration of B. Next, we need to make sure that we take the coefficients next to the A and B and attach them as exponents to our concentrations. So reactant A has a coefficient of 2 in front of it, which means we need to square the concentration of A, and reactant B has a coefficient of 1. So we just raise the concentration of B to the power of 1. So here's another hypothetical equation. Let's try finding the rate law for A, B, C, and D. So the first thing I'm going to do is set up the rate for A. So negative rate of A equals K, and note that it's still A here as our subscript on the rate because A is our first reactant. Now the concentrations are going to include A, B, and C because all three of those are my reactants, and I have to multiply their concentrations by one another. The last thing I have to do is make sure all of the coefficients become exponents. So A has a coefficient of 1, so Ca gets an exponent of 1. B has a coefficient of 3, so Cb gets the exponent 3, and C has a coefficient of 4, so concentration of C gets the exponent of 4. This is my rate law for A. Now if I want to find the rate law for my other reactants, I need to equate the chemicals like we did earlier. So remember the first thing we do to equate our compounds is just write out rate of each chemical is equaling one another. Rate of A equals the rate of B equals the rate of C equals the rate of D. Then we put positives and negatives on each rate depending on if it's a product or a reactant. A, B, and C are reactants, so they will get negatives, and D will stay positive as it is because it's a product. Next, we need to divide each rate by its respective coefficient. Compound A has a coefficient of 1, so we will divide the rate of A by 1. B has a coefficient of 3, C has 4, and D has 5. Now, in order to find the rates of B, C, and D, all I have to do is set them equal to one another. So first, I'm going to use the relationship between the rates of A and B to solve for the rate of B. And we can keep it negative rate of B because B is being consumed as a reactant. So I'm going to multiply this 3 over to the other side, and we get negative 3 rate of A equals rate of B. Now to find the rate of B, it's going to be negative 3 times the rate of A. This is the rate of B. Let's do the same thing to find the rate of C. Now I'm going to use the relationship between the rate of A and C to find the rate of C. If I solve for the negative rate of C, I get 4 times the negative rate of A. Recall that the negative rate of A was equal to K times Ca, so this is our negative rate of C. Now to find the rate of D, I'm going to equate the relationship between the rate of A and the rate of D. Solving for the rate of D gives negative rate of A times 5. So we are going to multiply 5 times the negative rate of A. So just being given a chemical reaction, this was an example of how you could find the rate law of one compound and equate all the rates to get the rate laws of all the other compounds. So let's look at this example. We need to write the rates of disappearance and the rates of appearance, which is formation or generation, for each species in this reaction. Let's start with the rates of disappearance first. I'm going to write out rate of A, B, C, and D without putting any positives or negatives on them first, just to cover all of the compounds that are present. So going back to these rules that I had talked about earlier, let's go through the rules and assign positives and negatives to our rates. So this diagram here that I was talking about earlier is going to help us figure out the signs of our answers. But when we talk about rates of disappearance, we are going to put negatives in front of all of our rates, just when we talk about the variable. And when we talk about the rate of formation, all of the variables for rate will be positive. Now when we actually plug in the number for 10 moles per second per meter cubed, we are going to use this table to determine the signs. Now let's look at the rate of disappearance first. A and B are reactants. So looking at the question, they tell us that we have a rate of 10 moles per second per meter cubed, which is consistent with the units I talked about earlier. Chloral is going to be assumed to be our first reactant, because it says chloral is being consumed when reacting with chlorobenzene, which we are going to assume to be our second reactant, to form DDT and water. So DDT is C and water is D. So the rate of chloral, A, is 10. So we know that the rate of A is 10. However, we don't know if it's positive or negative. Rate of disappearance for a reactant is going to be positive. So this is going to be a positive 10 moles per second per meter cubed. Rate of formation for a reactant is going to be negative. So the rate of formation for A is going to be negative 10. Now we need to use the equation we did. Now we need to equate our rates like we did earlier in order to find the rate of B, C, and D. I'm going to set the rates equal to one another like I did earlier and put negatives on our reactants and keep the positives on our products and divide them each by their coefficients. Now that I have the rate of A is equal to 10, the rate of A, C, and D are all in a 1-to-1 ratio. So I know that the rates of C and D are going to be 10 as well. However, the sign is going to be flipped. These will be negative because C and D are products and they are not disappearing. They are actually being formed. If we look at our cheat sheet, the rate of disappearance for a product is going to be negative. The rate of formation for products is always positive. So these are going to be positive 10. Now B is the only compound that is not in a 1-to-1 ratio with A. So I am going to equate the relationship between the rates of A and B, like I did in the last problem, and solve for the rate of B. The negative rate of B is equal to 2 times the negative rate of A. So now that I know the negative rate of A is 10, that means the negative rate of B is equal to 20. For the rate of formation, the value for B is going to be negative, just like it was with A, because A was also a reactant. All of these units are in moles per second per meter cubed as given up here. Now let's talk about concentration, molar flow rate, and mole time profiles. I just wanted to quickly introduce you to these graphs and what they mean. Now assume we have a reaction from reactant A to product B. So these graphs are all based off the basic reaction A goes to B. Now let's look at the concentration profile here first. If we have a reactor in which species A is initially poured in, over time, we know that our reaction is going to produce product B. So these molecules of A are going to turn into molecules of B. This is why Ca0, the concentration of chemical A in the beginning of our reactor, is very high. And over time, it starts to decrease exponentially because product B is actually being formed, which is not shown in the graph. So chemical A is being used up to form chemical B. Over time, the concentration of chemical A will decrease, but the concentration of chemical B will increase. Now let's look at the molar flow profile. This is almost the same. The flow rate of chemical A starts very high, and over time, it exponentially decreases. Now we look at this graph where the flow rate of B increases because B is being formed while A is being used up. The same thing happens if we look at the number of moles of A versus B over time. The moles of A decrease over time as they are used up to form product B. We can set up equations for mole balances to find the number of moles flowing in, flowing out, or moles generated or accumulated in our system volume during a chemical reaction. In order to do a mole balance, we need to set a boundary or a system volume where our reaction takes place. Say we have a reactor with moles flowing in and moles flowing out. This would be our system volume because this is where the reaction is taking place. Now that I drew this diagram, I can label all of the other variables that we're going to be using. This equation up here is the general mole balance. So let's talk about all the different variables that come into play. Note that all of the variables are measured in moles per time. All of these little subscripts J can also be called A or B or C or whichever chemical compound we are talking about in our reaction. So the first variable of our mole balance is the flow rate of chemical J into the reactor, which is Fj. And it has a little zero, which is called naught, which means initial flow. Next, we have Fj, which is the final flow rate out of the reactor. Then we have G sub J. G represents the amount of moles that are generated through the reaction in our system volume. For our last variable, Nj is the number of moles of species J. We have to take the derivative of this variable because it can change with time. So the number of moles of species J at time t. A lot of questions would be steady state, in which variables don't change per time. Anytime you have a system volume at steady state, this entire term will go to zero. Otherwise, if that's not stated, then we will need to keep this term in the equation. Although this is the general equation, we are going to discuss how it's going to change with respect to the various reactors. There's one more thing I want to discuss about the generation of moles. Now, I just want to elaborate a bit more on G. There is an equation that we can use to find our G value if it's not given to us directly in the equation. Sometimes when we look at a reactor, we assume that the reaction taking place inside is perfectly mixed, which means that inside the reactor, every variable, such as the rate of the reaction or concentration, is going to be uniform throughout the entire reactor. In reality, this is usually not the case. And sometimes if they don't tell you, or if you can't assume that your reactor is perfectly mixed, then you might come across the situation where at different points inside your system volume, so say this was our reactor, at different points inside your reactor, the rate of the reaction is going to be different, which means the rate of generation of moles of chemical species J is also going to be different. In that case, we need to use this equation here, where we take the integral over our volume of the rate of species J with respect to volume. And that is what we are going to sub in for G. Now, when we sub in the integral for our generation term, this is the final mole balance that we obtain and the equation that we will be manipulating in order to obtain the balances for different types of reactors. The first type of reactor we are going to talk about is a batch reactor. Some characteristics of batch reactors are that they are not at steady state, which is going to come into play in our mole balances. They're usually used for small-scale operations, such as making expensive products or testing new processes, and there is no flow in or out of the reactor. So going back to our original mole balance, we can cross off the first two terms because we do not have any flow in or out of the reactor. So this equation that's left over is our mole balance on a batch reactor. So we can also rearrange this equation to find time. dnj is the change of moles in the system. We can find the time that it takes to get from number of moles at point A to point B. This part can also be rewritten as 1 over negative RAV. So it is the integral of this portion with respect to Na, which is the number of moles, Na0 to Na1, initial to final. The next type of reactor we're going to talk about are semi-batch reactors. Semi-batch reactors have properties in between those of batch and continuous reactors. We will discuss continuous reactors next. They are unsteady state reactors. They have some flow in and out of the reactor, unlike regular batch reactors, but that flow is intermittent. So at some period during the course of the reaction, reactants may be put in or products may be taken out, but it is not a continuous flow like we will see next with the continuous flow reactors. Usually, semi-batch reactors are used to enhance selectivity of our product. So at the end of a reaction, you don't always achieve 100% of the product you want. There is usually some undesired product made. The ratio of moles of your desired to your undesired product is your selectivity. And obviously, you want to have the highest amount of desired product, so we use semi-batch reactors to enhance our selectivity. Without going through all the math, one of the main equations that you should know for semi-batch reactors is the differential of the concentration of species A with respect to time equals the rate of reaction of species A minus the initial volumetric flow rate divided by volume times the concentration of A. The next couple types of reactors we're going to discuss are continuous flow reactors. There are 3 different reactors that will fall under this category, and all of them assume steady state, which means there's no accumulation of moles or mass inside our reactor, and our accumulation term will equal 0. And there's perfect mixing, so our concentration and other variables will not vary with position inside our reactor. Unlike batch reactors, continuous flow reactors have a continuous flow of reactants and products into and out of the reactor. The first type of continuous flow reactor is a CSTR, a continuous stirred tank reactor. This is normally used with liquid phase reactions, and it is also known as a vat or backmix reactor. Using our general mole balance, we can cancel out the last term because it's at steady state. Because of perfect mixing, we can also take the integral out of this term and just multiply it by volume instead of the integral with respect to volume. And in doing that, we get this is the general mole balance for a CSTR. We can use an equation to rewrite the flow rates in terms of concentration and volume. F is equal to concentration times volume. So the flow rate in moles per time, such as moles per second, is equal to the concentration in moles per volume, such as moles per liter. V with the dot is volumetric flow rate, which is volume per time. Now, if you're trying to solve a problem and you don't have the initial or final flow rate, you can always substitute the initial concentration times volume and the final concentration times volume. If you do that and you isolate for the volume, you would end up obtaining this equation. The next type of continuous flow reactor we're going to talk about is a plug flow reactor. This is usually used for gas phase reactions, and I forgot to mention earlier that whenever we have a reaction that is in completely one phase, such as only liquid or only gas, it's called homogeneous. So reactants flow through tubes in this type of reactor, as this picture shows here. The reactants go in from one end of the pipe and come out the other. So we assume that the concentration and rate of the reaction vary in the axial direction through the reactor. Axial means parallel to the axis, which means in the x direction in this case. Although I won't go through how to derive the mole balance here, same way we did our mole balance earlier, except note that for continuous flow reactors, our accumulation has always been 0. The other thing that's different is that our volume out now includes a differential volume. That means we're trying to take such a small cross-sectional sliver of this reactor, which can be called our delta V, such that there will be no variations in our variables in that tiny, tiny sliver. And we're basically taking the mole balance of each tiny cross-sectional sliver of the reactor until we end up with enough slivers to make up the entire volume of the reactor. So all they did was rearrange the equation here and then take the limit of all of those tiny slivers to arrive at an answer. So this is the final mole balance that we arrive at. This is the differential of our final flow rate with respect to volume is equal to the rate of the reaction of species J. And in case we wanted to solve for volume, this equation can be rearranged and integrated to give us this. Volume is equal to the integral of -1 over RA with respect to flow rate. This can also be written as this. So the 2 important equations that I would take away for PFRs are these 2. What we're going to talk about is a PBR, a packed bed reactor. These are usually used for heterogeneous reactions between liquids and solids. The reaction takes place on the surface of a catalyst that is inside the reactor. The greater the mass of the catalyst, the greater the surface area there is for the reaction to occur. The only difference between a PFR and a PBR is that the reaction rate is now with respect to the mass of the solid catalyst, which is called W, rather than V, the volume. So here are a couple of differences between the PFR and PBR reactions. I'm not going to write down all of the PBR reactions because they are the same as the PFR ones with just a couple changes. So if you go back to your PFR reactions, replace all of the V's with W's because now everything is with respect to the weight of our catalyst, not with respect to volume. So the heterogeneous reaction rate is written as negative RA with the apostrophe on top, negative RA prime. Because this reaction is heterogeneous and used for liquid-solid reactions, so two different phases, usually in all of our other reactors we've used negative RA, which was the homogeneous reaction rate, because our other reactors were only using either gas or liquid phase reactions. So everywhere you see a negative RA, you're going to replace it with a negative RA prime. So the last point is a new equation that you can use to relate the homogeneous and the heterogeneous reaction rates with one another. So negative RA is our homogeneous reaction rate, which we discussed earlier is in units of moles per volume times time. This T is supposed to be the Greek letter rho, which means density. Density cat means density of our catalyst, which is in units of mass per volume, times negative RA prime, which is our heterogeneous reaction rate, or the reaction rate in our PBR. The only thing that's different between the units of RA and RA prime is that in the denominator of RA prime, we are now looking with respect to mass rather than with respect to volume. Now let's try to solve this example using what we've learned. The first question asks us to sketch the concentration profile. Concentration profiles are usually seen with volume on the x-axis and concentration on the y-axis. The x-axis goes from 0 to the entire volume of the reactor, and the concentration goes from 0 up to the initial concentration of reactant A. Note that when we draw our concentration profiles, by default, I'm just going to be drawing it for reactant A because they haven't specified, and usually if there was more than one reactant, all of them would have a similar exponential downward curve. Ca0 is the concentration entering our reactor of species A. This is the highest that our concentration of A is going to be, because once it enters the reactor, reactant A will start transforming into product B, and we will never have as high of a concentration as we do at the very beginning when we first feed in reactant A. So once we feed in reactant A, the concentration is going to exponentially decrease while the reactant A begins to transform into product B. There will likely still be a little bit of unreacted compound A at the very end of our reaction. However, most of it will have been transformed into B. This is a pretty generic graph, but that's usually how concentration profiles will look. The next part of the question asks us to derive an equation relating the reactor volume to the entering and exiting concentrations of A, the rate constant K, and the volumetric flow rate V0. First thing we need to see is what kind of reactor we're using. We are told that we are using a tubular reactor, which is otherwise known as a PFR. The first thing we're going to do is write out the mole balance for a PFR. Many of the problems in this course follow the same steps. We always want to start with a mole balance. And our mole balance is going to be dFA for species A over dV equals rate of A. The next thing we want to do is write out the rate law, which should always be our second step. Remember, rate law is usually always based on the first reactant, and in this case, our only reactant, A. Negative rate of A is equal to K times the concentration of A. And remember that the coefficients in front of A become exponents on this concentration. However, it's just a 1 in this case. The next thing we should do is write out other equations that we know that might help us. I mentioned this equation earlier in relating flow rate with concentration and volume. The flow rate of A is equal to the concentration of A times volume. And we're also given that the volumetric flow rate is constant. So we want to derive an equation relating the reactor volume to the entering and exiting concentrations. Whenever we want to derive an equation, we usually start with our mole balance, and then we make the rate law, and we have any other equations. We substitute them into our mole balance in order to manipulate it. We want an equation that relates the reactor volume to the entering and exiting concentrations of A. Right now, our mole balance is in terms of flow rate, not concentration. So that does give me a hint that I should probably substitute Ca times V instead of Fa. Once I substitute in the equation for Fa, I obtain Ca times V in my numerator. We know that our volumetric flow rate is constant, so our initial volumetric flow rate is equal to the volumetric flow rate anywhere inside our reactor. So instead of V, I'm going to put a V naught here because our question asks us to relate the reactor volume to the volumetric flow rate V naught. Because V naught is a constant and it's being multiplied by the concentration inside of these brackets, I'm going to move it outside of the brackets so we don't have to take the differential because it's just a constant. Now, because the equation mentioned that we also should include the rate constant K, I'm going to sub in our rate law, so positive RA would equal negative KCA if I bring the negative over. Now we should make sure that all of our CA terms are on one side because we have this differential on one side. So I'm going to bring dV over to the other side and bringing K, which is our constant, over to the left. And dCA will then be divided by CA, which I'm bringing over to the left as well. Our question asks us to relate the reactor volume to the entering and exiting concentrations of A. So the volume is 0 and the initial concentration is Ca naught. So our concentration of A is going to be Ca naught at the entrance to the reactor. And our reactor volume is going to be 0. So to solve this, we are going to integrate both sides. I'm going to pull this constant out of the integral, and I'm going to rewrite it as 1 over Ca. The integral of V is just going to go from 0 to the entire volume, and the integral of concentration is going to be from initial to final, Ca naught to Ca. So the constant goes on the outside, and by integrating 1 over Ca, we obtain the ln of Ca from Ca naught to Ca, and we obtain the volume from 0 to V, which is just going to be V. So I'm not going to go through the rules of integral calculus, but we're going to sub in the upper and lower limits into our equation to calculate our overall integral. I'm going to use our logarithm rules to convert this subtraction into a division statement, and I'm going to multiply through by this negative sign, which flips the sequence of my ln. Now, this is the final answer we get. Our question initially asked us to derive an equation relating the reactor volume, so it makes sense that it should be V equals something to the entering and exiting concentrations of A, which would have been Ca naught and Ca, the rate constant K, and the volumetric flow rate V naught. All of the variables that we have in our final equation were the ones that we were asked to use. The last part of the question says determine the reactor volume necessary to reduce the exiting concentration to 10% of the entering concentration. Let's write down all of our given variables first. We are looking for V1, and we want our final concentration at that point to be 10% of our initial concentration. And this equation relating the two is given right here. When the volumetric flow rate is 10 decimeter cubed per minute, and remember that they had told us that volumetric flow rate is constant, so V naught is equal to V. And they gave us the reaction rate K, which is 0.23 inverse minutes, or minutes to the negative 1. So we are trying to determine volume. They gave us the relationship between the initial and final concentrations. They gave us volumetric flow rate and the rate constant. So it looks like we just need to sub these into the equation that we calculated, the equation that we found in part B. Make sure that all of your units match up. The volumetric flow rate is per unit of time in minutes, and K is inverse minutes. Although we are not given the initial concentration, once we substitute 0.1 Ca naught in for the Ca naught will end up canceling out with one another. So we end up getting 10 over 0.23 times the ln of 1 over 0.1 will give you volume. And plugging this into our calculator gives 100 decimeter cubed. And that's the final answer. So that's all for today. I hope this video helped in learning about rates, the rate law, and mole balances, and how to apply them to kinetics problems. Leave a comment if you have any questions, and I will be leaving a link in the description below to the related blog post on my website, thestemtutor.org. Thanks for watching, and bye for now.